So this is what we have learned in the last class. We have seen up to this that the okay in the earlier class we have just looked at the differences between O-ray and E-ray, but this also gives you the properties of O-ray and E-ray also, because sometimes a question may be asked on what are the properties of ordinary ray and extraordinary ray. So even though I'm writing as the differences, these are also properties of ordinary ray and extraordinary ray. And we suppose that along the optic axis, the ordinary ray and extraordinary ray travels with the same velocity. Okay, that's why their wavefronts are, if you say it, since the ordinary ray obeys the laws of refraction, it moves with the same velocity in all the directions. Therefore, it covers equal distances in equal time. Hence, its wavefront is a spherical wavefront. Whereas in case of extraordinary ray, the velocity of extraordinary ray within the crystal is different in different directions. Therefore, in some directions it will move faster, in some directions move slower. Hence, its wavefront is an ellipsoidal wavefront. That's what we have learned in the last class. But I have added few more points also. There are some crystals called as negative crystals. For example, as a calcite and tourmaline. In negative crystals, if you take, it was observed that the extraordinary ray moves faster than ordinary ray. But in some cases called positive crystals like quartz, topaz, etc., E ray moves slower than O ray. So therefore, as E ray is moving faster, if you see here, okay, E ray is moving faster, but the condition is that along the optic axis they should have same velocity. Therefore, from the center, if you take any center from here, okay, from this point of it, both E ray and O ray are traveling with the same velocities. Therefore, they touch each other along the optic axis because their velocities are same. Along the optic axis, both of them will move with the same velocity. Hence, they are touching along the optic axis. But in other directions, O ray will cover same velocity, therefore it is a spherical. But E ray moves faster in some directions, therefore it is elliptical wavefront. Hence, in okay, if you say in crystals, negative crystals, hence okay. So we are writing here for negative crystals. This is negative crystals. Negative crystals. Examples we have given as a calcite and tourmaline negative crystal. If you take it, E ray is moving faster than O ray. Therefore, the wavefront of E ray is outside, whereas the O ray is inside it. Since E ray is moving faster. But in case of a positive crystal like quartz and tourmaline, E ray moves slower. So, but along the optic axis, they move with the same velocity. Therefore, along the optic axis, they are touching each other. At the optic axis, they are touching each other. But in case of a positive crystal, if I take a positive crystal like quartz, positive crystal, this is a positive crystal. Inside the positive crystal, if you take it, the O ray moves faster. Therefore, it is outside. It's covering huge, okay, more distance. Whereas this E ray, even though it is still elliptical, it is inside the spherical wavefront formed by O ray. Hence, the O ray is inside since it is moving slower than O ray. These are the different properties of O rays and E rays in positive and negative crystals. But you should remember that along the optic axis, they will have same velocity. Therefore, they touch each other. They are touching each other. Here, they're touching each other. This is the optic axis direction. Here also, this is the direction of optic axis. Therefore, they are touching each other. Hence, we say that the sphere and ellipsoid touch each other. Okay. So if you want right here, touch each other. Okay. each other along the direction of optic axis. Now, the anisotropic crystals which we have discussed here, if you want to segregate them, crystals may be isotropic having same properties in all directions, or anisotropic having different properties in different direction like velocity of light, refractive index, etc. They will be different in different directions. And therefore crystals can be segregated isotropic or anisotropic. And these isotropic and anisotropic crystals, if I take it, they can be taken as positive crystals or negative crystals. That means here actually the anisotropic crystals, I can write it as positive crystals or negative crystals. And positive crystals, we have seen that E ray moves faster and E ray moves slower, and negative crystals E ray moves faster. And these crystals again can be classified positive and negative crystals as two categories as uniaxial crystals and biaxial crystals. Okay, so this is again uniaxial crystals and biaxial crystals, meaning that the optic axis what we have so far not defined will define what is actually the optic axis is. For uniaxial crystals there is only one optical axis or one direction of optical axis. So therefore we say that in uniaxial crystals, uni means one, uniaxial crystals, there is only one direction, because optic axis we don't say it's a line, we call it as a direction, is only one direction of optical axis. So along that optical axis the E ray and O ray moves with the same velocity. So therefore in uniaxial crystal there is only one direction of optical, or we say instead of optical I write it as optic axis. Optic axis. That's why we are calling it as one is there we are uniaxial. So if you take biaxial crystals, in biaxial crystals there are two, bi means two. So two axes will be there along which E ray and O ray moves same velocity. In biaxial crystals, there are two directions of two directions for optic axis. Hence we have crystals isotropic and isotropic. In isotropic we have positive and negative crystals, and these positive and negative crystals may be uniaxial or biaxial crystals. Now we look at what is actually the plane of polarization, plane of vibration, principal section, and how to see the crystal structure of calcite, because we have given here one of the best utilizing crystal is calcite, which is a negative crystal. So we will look at the crystal structure of calcite, and we'll also see some of the important definitions. So we will now look at this. Here is a plane of polarization, and also we'll see plane of vibration, and plane of vibration. So in a polarized light, we have vibrations confined to a particular plane. So which plane vibrations are there? That plane actually we call it as plane of vibration. So therefore, to understand plane of vibration, here I draw a simple figure to see what is plane of vibration and what is plane of polarization. First, we look at plane of vibration. Plane of vibration, where the plane containing optic axis and the direction of vibrations, we call that as a plane of vibration. So therefore, for example, I take here an unpolarized light like this in all directions, and we call it as unpolarized light. And this unpolarized light is made to fall on a crystal, a cut, or a device which we call it as a polarizer. So I am taking here a polarizer, and the polarizer will have an axis. This is an axis for it. We call it as polarizer axis. And this device is polarizer. And once light incident on the polarizer, the light transmitted by it will have vibrations only parallel to optic axis. So therefore, it is a plane polarized light coming out from the one. So this is, of course, we call it as optic axis. Optic axis. Now I take here a plane, okay, containing so this is the plane I am taking here. The plane what I am taking here is this plane. This plane I am considering. This is the plane I am taking. Okay, and if you see it, this is direction of propagation. Okay, this is direction of propagation if I take it as. So now we'll define in this plane. If you take it, this plane contains, okay, vibration of the polarized light. This is the vibration of the polarized light, and okay, also we say the optic axis. So therefore, a plane containing direction of vibration as well as direction of propagation. This is direction of propagation. Direction of propagation. So the direction of propagation is, and also the direction of vibration, they are in this plane. So this plane we call it as plane of vibration. This plane we call it as plane of vibration. Otherwise we'll say show that, okay, the green light whatever I have drawn here, we call this green plane as plane of vibration. So a plane containing plane containing a plane containing direction of vibration, direction of vibrations. So these are the vibrations, okay, E vector vibrations, they are in this plane, and direction of the vibration, and as well as you can say as well as the direction of propagation, direction of propagation is called plane of vibration. Plane of vibration. So this is the definition where the vibrations are confined to the plane. We call it as plane of vibration. Okay. Now similarly, we define the plane of polarization. So plane of polarization is the plane, okay, this is the plane I am taking, which is again containing direction of propagation but perpendicular to plane of vibration. Therefore, here I draw a plane something like this. Suppose this is the perpendicular plane I am drawing. This is the perpendicular plane I am taking. Okay, this is going like this, and this plane which is perpendicular to plane of vibration, this is the plane of vibration we have written, okay, to this I am taking the plane, and this plane we generally call as the plane of polarization. This is the plane I am taking. So this plane which is perpendicular to plane of okay, uh, vibration and also direction of propagation. So therefore we now define the plane of polarization as plane containing direction of propagation, or passing through, you can say it, containing direction of propagation. Okay, direction of propagation and perpendicular the to the plane of vibration, plane of vibration is called, okay, plane of polarization, plane of polarization. Understood? Okay, can you able to see the screen, whatever I am writing here?
Yes, sir.
Yeah, so this is plane of vibration. So we have to see in plane of vibration, we have only vibrations of E vector. But in plane of polarization, vibration vectors are not there. Okay, it's a perpendicular plane not containing this. So thereby we draw this as whatever we have used the red color plane. That plane is actually this plane. If I want to draw, this is plane of polarization. Plane of polarization. So we have plane of polarization and plane of vibrations. These are very important planes to understand. Now we will look at what actually is this optic axis and what are these planes of principal plane of okay, principal plane of a given crystal. So now we to know that we should know first the crystal structure of any of these crystals like calcite, quartz, etc. Now I'll just see geometry of calcite crystal. Calcite crystal. And from this, we will now define principal section and what are the angles in the principal section also will define geometry of crystal structure, okay, or crystal structure of calcite. So what is chemically, the chemical name, if what I take it chemically, calcite is simply hydrated, okay, hydrated calcium carbonate. It's simply calcium calcium carbonate. That is, calcium carbonate is nothing but CaCO3. So chemically, it is a this structure. We'll take it. So chemically, it is hydrated calcium carbonate. But what is the structure of it? This is okay. Calcite is also known as Iceland spur. We also called as also known as Iceland spur, because these crystals are naturally occurring in Iceland in large number. The country Iceland, you might have heard about Iceland. That's why we call it as Iceland spur. Spur is a crystal. Okay. So, but what is the geometry? What is the crystal structure? Generally, these calcite crystals are available in the structure called rhombohedral class of hexagonal system. So crystal structure is, if you want to write it as, it belongs to rhombohedral, okay, rhombohedral class of, if I take it as rhombohedral class of hexagonal system, hexagonal system. It is about, but quartz, if you take it has a quartz crystal structure, that is really part different. Okay, so it's a hexagonal system, like, and because it's a rhombohedron, all phases, whatever you take in the rhombohedron, they are parallelograms. Therefore, we say that here all phases, what are the phases you are taking or what are the planes you are taking, because in a parallelogram there are 6 phases. So all 6 phases of, okay, the rhombohedron. Okay, rhombohedron structure. If you take it, all six faces of rhombohedron are parallelograms. Parallelograms. Therefore, okay, parallelograms. Hence, I draw here what are the angles in this and how to see these structures. To draw the structures of this one, I take a parallelogram. Okay, I just draw a parallelogram here. This is the parallelogram I have taken. Okay, 1 minute. I'll go for it. I'll take a parallelogram. This is the parallelogram I am drawing. Okay, and then to make this a parallelogram, I just take it and just draw it. So I'm drawing the parallelogram. All places are, as I said, it is okay. This is the parallelogram I'm taking. I just keep it like this. So to draw this parallelogram, I am taking this crystal like this. Then I join this corner. I join this corner, and I also join this corner. Okay, this corner I'll join it. 1 minute. So you also draw the structure of this particular calcite crystal. It's a parallelogram. So I'm drawing all parallelograms here. Okay, this is the parallelogram I'm taking. And now I choose two corner points here. This is the corner point. I call it as point A. I call this as a point A. So I call this as this corner point as A point. And the opposite corner point, this I'll take it as B point. A point and B point. Now, these parallelograms in the calcite crystal, they join at point A and also point B in a specific and particular direction, or the orientation we say it. And it was found that the three faces joining at point A, that means this angle, or if you take this angle, okay, this angle, or if you consider, okay, uh, this angle, all these faces which are meeting at this point A, they meet at an angle equal to 102 degrees. This is 102 degrees, and this is also okay, 102 degrees. But what is the angle, this angle? Can you tell me what should be this angle? This angle or this angle? Anyone? Can you tell me what is
78.
this? 70?
8.
Yeah, good. So this angle is 78 degrees and this angle is also 78 degrees. Okay. So calcite crystal will have now this. But what is the name given to an angle more than 90 degrees? More than 90 degrees. So we call this angle, which is more than 102 angle, more than 20 degree, 90 degrees angles, we call it as obtuse angles. Yes, you know obtuse angle?
Yes.
And the other angles, what we say, we call them acute angles. These obtuse angles. So there are 2 points A and B at which the planes will join. Okay, the planes will join at obtuse angle. So that means if I take suppose say 45 or less than 45, this angle it is very sharp. If you take 90 degrees, the sharpness decreases. If I take somewhere more than 90 degrees, the sharpness of the angle still decreases. If I take 1 or 2 degrees or 1 degrees, the sharpness is decreasing. Okay, this is very sharp. If I take a small angle like this, it is very sharp. It's very okay, but the sharpness of the angle okay will decrease, and as you are increase the angle more than 90, this will become a blunt angle, will become a blunt angle because it is not sharp, it is almost a blunt angle, we call it as more than 90 degrees. Therefore here 1 or 2 degrees is joining, here also 1 or 2 degrees they are joining here. Okay, therefore point A and point B they are not very sharp, and therefore corner A okay we call it as blunt corner, and corner B also it's a blunt corner. Both of them we call them as blunt corners. So therefore we say that there are two opposite corners. Okay, A and B are opposite. These are opposite corners. If you take it, they are opposite corners. So therefore in a calcite there are two blunt corners. So blunt corners are nothing but the corners at which parallelograms will join at obtuse angle, and those are called blunt corners. Therefore, in calcite, there are two blunt corners A and B. Now, take any line, I am calling it as any line only, that is passing through point A. I am taking a line. It may be passing through point A or a line passing through point B. They need not be okay touching, and this line drawn from this point where three obtuse angles are meeting, and that direction of the line gives the optic axis, and this we call it as optic axis. So therefore we will now define what is a optic axis. These are A, corner B are called blunt corners because they are at obtuse angles. Hence now we will define optic axis. Optic axis. Remember that optic axis is not just a line just like XYZ axis, but it is direction. It is a direction means that any line drawn to x-axis parallel to x-axis is also an x-axis. Therefore, any line drawn parallel to optic axis is also a parallel axis. Hence, we write now optic axis as a line, okay, passing through any one of the blunt corners, any one of the blunt corners. Here we have two blunt corners. If you say here, I suppose that corner A or corner B are blunt corners where obtuse angle planes are meeting. Okay, a line passing through any one of the blunt corners and making this is very important. Okay, making equal angles with the three planes. Here three planes are, one plane is this, other plane is this, other plane is this, with the three okay faces or planes, with the three faces. I have now, this is the one space, one plane, this is another okay, plane, this is another plane. Three planes are there, or these planes are called three faces of a parallelogram, okay, or three planes of faces of a rhombohedron. So making equal angles with the three faces that meet faces that meet at these points, means at these blunt corners. We say at this corner, any one corner, therefore I can write this as, okay, at this corner, simply at this corner, okay. And this is not a line passing through any one of the blunt corners A or B and making equal angles with the three faces that are meeting here, that are meeting at this point A, that are meeting at point A. Okay, corner, locate the direction of the direction of optic axis. Therefore, you should remember that's the direction of optic axis. Okay, any line drawn parallel to optic axis, parallel to optic axis, or parallel to this direction, we say, is also an optic axis. Parallel to this direction is also an optic axis. So you may be having some, okay, uh, so confusion with the definition. What is the line? What is the direction? Therefore, we say another definition here, okay, uh, for principal section. Here optic axis is very clear. Any line at this corner, if you take it, this corner, if you draw a line like this line should make equal angles with all the three faces that are meeting. That line is only called as optic axis direction. So any line, because if I cut this into parts, okay, this crystal, if you take it, this is the crystal we are taking. And if I cut here, again I'll get this here. Again, if I cut it here, the blunt corner goes here. If I cut it here, the blunt corner goes here. Therefore, any line drawn parallel to that can also be taken as optic axis. So that is the optic axis we call it as. And now to see what is a principal section, that is important here. So now we will see a principal section. Okay. Principal section. So this is an important one to get a polarizer and an input, because we have defined that O ray will have vibrations perpendicular to principal section and E ray will have vibrations confined to principal section. But what is the principal section we have not defined. So I will define a principal section. To define a principal section is a plane I am taking. Okay, a plane, that a plane which contains optic axis, that means it should contain optic axis and a cut perpendicular to opposite. These are the two opposite directions of the crystal. So therefore I cut perpendicular to this. I'll cut it here. Okay, I cut here. Suppose say I take here. Okay, I'll take another color to show you very clearly. So I am taking a black color. So this is the cut I am taking perpendicular to this. Okay. So I take this here, and from this I'll take a cut and I join this two. This cut, whatever I am taking, okay, this is the cut I am taking from here. Okay, this cut plane, I'm cutting the plane, I'm taking it from this cross section, this plane. Okay, that plane is called principal section. This plane, this part of it, I should take it as a principal section. Therefore, I will now define the principal section as the plane containing the optic axis. In this plane, optic axis is there. You can see here. Okay, and perpendicular to opposite directions of the crystal, or opposite faces of the crystal, or perpendicular crystals of the opposite faces. We have to take it. So that we'll define it as principal section. So I write the definition of principal section as like this. Okay, any plane containing any plane containing the optic axis. Optic axis is the line that was passing through the blunt corners, any one of the blunt corners. So any plane containing the optic axis, and is perpendicular, okay, to the two opposite, I write it as opposite and it is okay, opposite faces is called principal section. So from this definition, if you once again you look at the figure, principal section, we call it as principal section. So you just go it here. If I go here, these are the opposite faces. This is opposite face. This is the opposite face. To this I am cutting perpendicular. This is the perpendicular cutting. I am cutting it perpendicularly. Okay. And this slice, if you take it, is a plane. And that plane is actually one. But see, it is perpendicular. But this is not perpendicular. Therefore, the angle is not okay. What we are cutting is 90 degrees to this. Therefore, if I take a plane like this, if 1 or 2 degrees in the principal section is not 1 degrees, it will change. Therefore, we say that if I want to draw such a figure for this principal section, I just take the cut. Okay, maybe one cut I am taking here, the other cut, the other one I am taking a cut from this plane. Okay, and I take here another cut from here. Suppose say, okay, I'll just move it. And then I'll just take it same as that previous one. Okay, so I'm moving it. So I'm taking like this. These are the perpendicular cuts. Then I join these corners, this corner, and also this corner and this corner. Okay, I have drawn these corners. Now, otherwise, if you want to see in different direction also, because the orientation is slightly different, I can take different orientation out to show you what exactly this becomes. Okay, so I now take something like a cube so that you can understand easily. One cube I'll take it. Okay, then I take another cube. Okay, something like this. I take it is like this. This is another cube I'm taking. Then I join these corners. This corner, I join this corner. I'll join this also. I'll join the corners. I get like this slice cutting from that. Okay. From that, if I take this axis that is passing from the blunt corners, this is the blunt corners that is going. So if I can draw any of these lines parallel to this is another line parallel to it, and I can draw another line parallel to this. Okay, these all are optic axes. So therefore, if I want to show the exact location of the optic axis, okay, and a principal section in this, if this is the crystal, calcium crystal I have taken it, our cut, whatever you are taking the cut, is in such a way that in this one, if I take it, okay, I'll draw here. I'll take the cut in such a way that I draw here again the same, okay, or I can show you something like this. The This is the surface, top surface I am taking, okay. I extend this, okay, so I'm slowly drawing it and extend this, and I extend this also. I'll get this, join it and extend this, and I'll join it here. And the back face also I have to draw it. This is the black, okay, the back face of this crystal. I'll take like this. From this I have to cut in such a way that that one will be, suppose say this I call it as A, this I call it as B, okay, so the opposite one is B, AB blunt corners, then I call this as C and a D. Then I have to take a plane from AC, okay, to BC and like this. This plane will be perpendicular section. So therefore, this section we call it as principal section. So, but in general, these principal sections are shown something like this. Okay, so I'll show you the principal section by drawing a parallelogram. So those parallelograms, if I want to say it, I will write them something like this. Okay, just a minute. Okay, I'll just see it like this. Now I'll draw the principal section something like this. So the principal section will have, okay, so I'll draw principal section something like this. Otherwise, okay, I'll just go for this and I take it and I draw the principal section something like this. This is actually the principal section. So whatever you are taking from this cut, okay, this cut is principal section. So I take that principal section something like this, okay, and from this we will say that this is corner A. I'll write this as a corner A, blunt corner, and another blunt corner I call it as B, and I'll call this and this as CD. Now, whatever the line that is passing from any one of the blunt corners and going like this, okay, generally we call it as a principal section. So therefore, I now draw the principal optic axis likewise. You go from A and it has to go to B. Okay, need not be B, and it can be parallel to this line also. This line we call it as optic axis. Optic axis. And we'll have now, because we have cut made by 8, this angle will now become 109 degrees instead of 102 degrees. See here, we have 102 degrees thus. But these faces are aligned with obtuse angles, but cut is at 90 degrees. So therefore, this 90 degrees cut, whatever you are taking this cut, will not make you 102 degrees here. Okay, therefore if this you take it a perpendicular cut, this will not be 102 degrees because we are taking, okay, a perpendicular cut there. Therefore in the principal section we don't have 102 degrees. This is not 102 degrees because the perpendicular cut from the opposite faces, which are a parallelogram type of faces meeting at different angles. So therefore the cut will not have, okay, 102 degrees, will have 109 degrees, and okay, so 102 degrees, that is the change to this, and therefore this will be 71 degrees. Okay, we'll have like this. So therefore we say that in principal section, the angles are not 1 or 2, and this in principal section the angles are 109 and okay, we'll say 71 degrees. This is important because from the calcite crystal we take a slice, whatever I have shown like this, and this we call it as principal section, and that principal section crystal cut acts as a polarizer or analyzer. That's why we have defining all this. Okay, therefore we have now this is a principal section. So this principal section, this we call it as principal section. And this principal section angles are very important, and the angles are 109 and 71 degrees. And these also will change it when you make this as a polarizer or a analyzer. And this you have to remember very carefully. And thereby we will now see how to construct a polarizer. And to construct a polarizer, we call that polarizer as Nicol prism. Therefore, now we will see construction of a polarizer. Okay, construction, and also we look at working, construction and working of a Nicol prism. Nicol is the name of a scientist who made this one by using a calcite crystal and made a small type prism type one. It is not actually the prism type one, it's a parallelogram type one. So we have Nicol prisms that are available. Whenever coming to lab, you can see some prisms made by doubly refracting crystals which are there in our physics lab. So construction and working of a Nicol prism, which is a very important an essay question for your examinations. Not only that, the construction of a Nicol prism is very useful to produce and analyze a polarizer light. So this is a device which produce Nicol prism. We call it as Nicol prism is a device to produce polarized light from, of course, an unpolarized light. Device to produce polarized light. But the advantage of this is that the Nicol prism can be used as a polarizer, and the same thing can be used as an analyzer also, which we have seen in the earlier classes. Nicol prism, okay, can be used as a polarizer. A polarizer is one which produces a polarized light from unpolarized light. It is as a polarizer and also as an analyzer. So therefore, the Nicol works as a polarizer and analyzer. Therefore, a question is again asked as explain the polarizer and analyzer actions of a Nicol prism. So what we have to do is that whenever you take a doubly refracting medium, what we have seen doubly refracting crystal, the property of the doubly refracting crystal is that whenever light falls on it, we know that it splits into two parts, and the two parts are having both are plane polarized, having vibrations in parallel direction and also perpendicular direction. This we call it as O ray, and this we call it as E ray. Now what I have to do is, when they are coming out of the crystal, this is coming, and this is also coming. When they are coming out of the crystal, again they will merge together and gives you a partially polarized light. Therefore, if you are capable of terminating one of the ray in the crystal itself, that means I do some construction, I remove this layer not to come out. If it is not coming out, if it is coming, then it is a plane polarized light. Otherwise, I take a crystal cut, doubly refracting crystal cut in a principal section, and if the light is falling on it, okay, and by falling the light on this, suppose say it is diffracted into two parts having vibrations in the perpendicular direction called O ray, and also we have E ray having vibrations parallel to this. Then what I do is I just take this O ray to be contained within the crystal. It will not come out, but this will come out. So therefore, the light that is coming out of the crystal is a plane polarized light. Likewise, a Nicol prism tries to stop, okay, or tries to remove one of the two plane polarized lights and allow only one polarized light to come out of the crystal. Therefore, it produces a plane polarized light from the unpolarized light. That is what here is more important. So therefore, the function of the Nicol prism is that, okay, it has to remove one of the light rays in the doubly refracting rays. If it is removing one E ray, then coming out is O ray is okay, plane polarized. Otherwise, we generally stop O ray not to come, and it is internally absorbed and will get E ray only out of it. Then we call that as a, okay, we call it as a plane polarized light. Therefore, Nicol prism works on the principle of total internal reflection for any one of the ray. If you are able to remove one of the ray by total internal reflection, you can get a polarized light out of two doubly refracting rays. Therefore, we now define, okay, that in Nicol prism, what it will do is Nicol prism by some means. What that means, we'll see in the next class tomorrow, the construction of it. Okay, so we'll say the Nicol prism eliminates one of the doubly refracting rays, doubly refracting, that is E ray or O ray is there, refracting rays. One of the, okay, doubly refracting rays using the phenomena of total internal reflection, total internal reflection, which we call it as TIR, total internal reflection. Nicol prism eliminates one of the doubly refracting rays using the phenomena of total reflection and allows only one, and allows, okay, and we say, okay, otherwise we say, and allows only one ray, that is generally E ray. Okay, O ray will be stopped. Okay. Allows only one ray to come or to transmit out of the crystal, out of the crystal. That's why we'll produce the total internal reflection. So for this, we require some special arrangement and construction to make ordinary ray to undergo total internal reflection. Okay, this is the principle what we have seen it. This is the principle of okay, nickel prism. This is the principle. Now, in the next class, we'll see the construction and working of the nickel prism. So tomorrow class, we'll see construction of it. Construction of nickel prism. How do I do the construction of nickel prism? And thereby we'll also see the working of nickel prism in the next class. Okay. So those who are having doubts in this class, you can now ask me and clarify your doubts.